Welcome to the next video in the systems programming series, still talking about chapter 2 of the textbook Dive into Systems, getting into section 5 on arrays in C. I think this is mostly about two-dimensional arrays in C. So I think here we just have a brief overview of things we've already discussed when it comes to dynamically allocated arrays. Here, a brief overview of, or if I said dynamically, I meant statically up there, dynamically down here. Here we're getting into, I think, some stuff that I mentioned before but didn't talk quite as thoroughly about. So this has to do with the address layout in memory of our arrays. Take, for instance, that you have this statically allocated array called iArray. It holds 6 integers. Now, this is statically allocated, but everything that we say about this will hold just as well for dynamically allocated arrays. And so let's just assume, for the sake of conversation, that the address of the array is at 1230. Now, what that kind of means, what is equivalent to that, is that the element at index 0 is also located at address 1230. So essentially, right, the point here is that the address of the array is the same as the address of the 0th element. In effect, this is what we mean when we say that the address of the array is the base address of the data or something like that. So anyway, now what's worth observing here is that when you increment to the next index, the 1th index, let's say, the address increments by 4, and that is because this is an integer array, and integers use 4 bytes, and these addresses are the addresses of bytes. So because an integer uses up 4 bytes, then to get to the next element, we increment by 4 addresses in memory. And, naturally, to get to the very next address, we increment again by 4 and by 4 and so on, every time incrementing the index only by 1, because the index tracks the elements. The elements, in effect, are separated or, take up the space of 4 bytes, and that's why the address increments by 4, when the index increments always by 1. Now we'll get into two-dimensional arrays. So for two-dimensional arrays, essentially, what this really is basically an array of arrays. We can think of it in this kind of row-column format, right? So here, 50 is the declaration, right? This is a static declaration. Later, we'll see how to do two-dimensional arrays dynamically. But for now, we'll see the static version of things. And here, the first index is treated as the rows. The second index is treated as the number of columns. So this is a 50 by 100 integer matrix. But another way to think about sort of what this is that the first thing, right, actually maybe it's worth thinking of it like this. What would you get if you said matrix 10, but without specifying the column? Well, this just is the entire 10th index row of the matrix, right? So this is some array, which is the columns of the columns that are located in row index 10. So, who knows what they are, but maybe it's, 7, 15, -2, whatever, so on. But the point is that when that it can be specified in a sense kind of one at a time, right? Although we usually write it all at once. If we want to write row 3, column 7, and get that one specific integer at that row and that column, we almost always just write it immediately. But I guess, there's some value in understanding that really what's going on is that we are first starting from this matrix, but that is an array of integer arrays. And we are getting the 10th one, or the 10th index one, which basically corresponds to getting an entire row, the 10th index row, made up of all of the columns along that row. And then from that row, we specify its 7th index to get one specific integer. So, okay, you can imagine that physically in hardware, these things are laid out in exactly this way, where, you know, like maybe addresses are running along this way and also along this way. I think we're going to see that that's actually not literally how it is laid out in physical, you know, space. But at least you imagine it looking like that. To use these things, often, right, a common way to loop over every coordinate of a matrix is to start with a for loop, looping over all of your row coordinates, and then for, you know, inside of that for loop, get another for loop, which runs over the columns, and this makes your progression through the matrix go in a row major way. So, you know, because you first fix I equal to 0, and then the next thing that you do is loop over j so that j becomes 0 and you're getting that 0, 0 coordinate. But the next thing that happens is that j becomes 1, so you're next getting that coordinate, and so on until you reach the end of the 0th index row, at which point the for loop for I kicks over, bumps up I to 1, and then we do it all over again. So that effectively, you know, doing it this way causes you to start in the upper left corner and progress horizontally from left to right. And it is possible to design this to progress through the matrix in several other different patterns. But this, right, usually it doesn't matter what order you do it in, as long as, you know, if you know what the order is, then you can do whatever you need to do. Often the order doesn't matter, but sometimes it does, and it's worth knowing how you're controlling the order in which the elements of the array are being accessed. Okay. Moving on to two-dimensional arrays, what is especially, not moving on to, but talking about how you pass them into functions. What is worth knowing here, what is really crucial to know here, is that when you pass a two-dimensional array as an argument to a function, you must specify the number of columns, but you do not have to specify the number of rows. And this has to do with how it, you know, organizes memory and so on. But so you must always, you are free to leave the first coordinate free. But you must specify everything after that, which is to say, in a two-dimensional array, the columns. Because you must specify the columns, you know, you could hardcode, you could just like literally write this as 100 if you knew that the columns were going to be 100. But very, very often, you change your mind about this kind of a thing, and so it's worth programming it into a constant global variable. So, and this is how you do that, right? So define it like that. This way, you call on that variable throughout the rest of your program, and if you ever change your mind, which I promise you very often do, all you have to do is edit it in one place. So that's a worthwhile thing to note. But okay, and then the next thing to talk about is, is it passed by value? Is it passed by reference? We saw before that when you pass an array into a function, it is actually passed by reference. It's sort of the one case in which C is passed by reference. Or you could say that it's passed by value, but the value of the array is the address. Okay, that doesn't strike, that seems to me slightly confusing, but you can think of it either way. I mean, but it just seems to me like it's more helpful and insightful to just say that it's passed by reference. In any case, so that's how it was with a one-dimensional array. And so what is it for a two-dimensional array? Exactly the same story. And so which address do you get, right? Which address is passed in when you, for instance, do a thing like this, where you pass in the array, the two-dimensional array? Which address is passed in? The address of the 0, 0 index element, right? So if you imagine that your array looks like this, and this is your 0, 0 coordinate. The address of that thing is the address that is passed in. But, at least for now, we don't really have to know that, because using these indices, it goes exactly the same. Just because it's passed in as an address doesn't really change how you access and assign values inside of the matrix. So in any case, but it will be worthwhile to know that. Also, just as when it came to arrays, you had to pass in the size of the array so that you could do for loops like this. Well, you don't have to hard code the number of rows, but you will want to pass that in as an argument. What that does is it gives you the flexibility. Down here, these two matrices have to be of the same columns in order to pass them into this function, but they are free to vary in regards to the number of rows, as long as you then pass that piece of information in. So the rows are a little more flexible. You do still have to keep track of the quantity, but at the very least you can have a single function passing various row quantities in. But that is not true when it comes to the columns, because the columns, you must basically hard code that into your function. I think I've covered everything here, so okay, let's move on. Here we'll look at how things, and this is specifically how things work in address space for statically allocated arrays. So let's take a look at this integer, two-dimensional, statically allocated array of dimension 3, 4. Now, how are all of the integers going to be laid out in memory? Well, we are still going to jump by the number of bytes that an integer requires. So that's still every address is incremented by 4. And keep in mind that, basically the first thing that it allocates is the first, right? Basically, two-dimensional arrays are stored in a row major way. So the first thing that you're going to get, right, the first collection of space in your hardware is going to be the space of row 0, then row 1, then row 2. So this is sort of the memory being tracked in a row major way, or something like that, however you want to say that. And of course, within each row, so this would be like a fixed row because the row index is 0 throughout, and the column index is incrementing. So now we're going to talk about dynamically allocating memory for arrays, and it's going to have the same sort of advantages and disadvantages of one-dimensional arrays, but there are going to be two different methods, and so maybe it's not exactly the same because there are these two different methods, and each one has its own advantages and disadvantages. Right, so there's going to be a single call to malloc. If you do this, then the picture, especially for the addresses in memory, is identical to the picture for a statically allocated array. The only difference being that because it is dynamic, you can free up the memory and make changes to your decisions later on. But this is significantly more complicated because when you malloc like this, you have to know the addresses of memory. It becomes significantly more complicated. Because it basically you have to deal with it almost as if it were a one-dimensional array. You'll see what I mean by that in a minute. But in any case, so basically, you can do it this way. When you do it this way, you get contiguous memory storage, and that causes a faster running program, but it comes with a lot of complexity for the programmer to try to track, what information is stored where. So anyway, the alternative is to make multiple calls to malloc, and here the code that the programmer writes is significantly easier. When you do it like this, you can kind of just rely on the indexing syntax to track everything for you. But when you make multiple calls to malloc, then each row may, and in fact generally will be stored in different places in memory, making your program run a bit smaller, or depending on the sizes of these arrays and so on, possibly even a lot slower. But so there are these two alternatives, and they come with various advantages and disadvantages. So here what we're going to see is the first method where we make a single call to malloc. Now, when you make a so we're going to do a two-dimensional integer array. We're going to do it by making a single call to malloc. And to do this, you say, okay, well, I'm going to be storing integers, right? So I need to malloc each thing as the size of an integer. How many integers in total will I need? Well, in any n by m array, the number of coordinates is n times n. So we have n times m integers, and then we multiply that by the size of each integer to say how much space we will need in total. Do your standard check to make sure that the malloc was successful. But now, right, so, and that's not that hard, right? I think that's fairly, sensible. And notice, by the way, that when we make our execution stack diagram, the stack is on one side, the heap is on another side, right? This is the heap over here because this was dynamically allocated. So it doesn't go on the stack, it goes on the heap. And so far, things don't look all that bad. But here is where you start to see the complexity that comes from doing this with a single call to malloc. Notice that because it is a single call to malloc, you have to basically treat it, right? Your indexing access and so on has to basically treat it like it is a one-dimensional array, even though you are trying to use it as a two-dimensional array. So what that means is that now there is only a single index. Does it make the, yeah, so what you would like to have is to treat it like it has two indices, one for the row, one for the column. But because you did only a single call to malloc, it basically doesn't know that, and you can't use this syntax. So what you have to do is say that so long as I'm using, right, or let's just put it this way. This is index 0, right? So the true index that you would write here is index 0. This is index 1. This is index 2, 3. And then where it starts to get a little painful is that this is index 4, right? Not, what you have to kind of think of as basically resulting from your row size, which is 4, times your row index, which is now 1, plus your column index, which is 0. And so the very next one is going to be 4 times 1 plus 1, and so on. And every time you go to a new row, like let's say that you're here, now your row index increments, so it's 4 times 2, right? Because each row holds 4 things, so 4 times 1 kind of covers this, 4 times 2 covers that. So by doing 4 times 2, that gets you up to basically here, and then plus your column index, which is 0. But anyway, so you basically have to perform this arithmetic yourself. And, in a small example like this, maybe it doesn't look that intimidating, but certainly as your programs grow in complexity, keeping track of these kinds of things can just create, some things that you have to calculate or think about that if you stored it in a much more two-dimensional way, or, if you could use the two-dimensional syntax, it would have been easier to think about. So, what this is saying is that we have row index I, we're multiplying by m, which is the number of coordinates within each row. By the way, that is the same thing as the number of columns. So that's why we're multiplying by m, the number of columns. So take your row index times the number of columns, and then add your column index. That's how you get to row I, column j. But if you did this by making multiple calls to malloc, then you could sort of recover the sort of like two-dimensional syntax used to access stuff in your array. But we'll see that later. Okay, and then there's also this conversation about how do you pass stuff around in functions, right, when they are two-dimensional integer arrays dynamically allocated. Here again, right, the The declaration is just like the declaration of the object itself. At least that's, I think you could even get away possibly with statically, writing the static type basically, but why not, right? Why not just go ahead and give it the int star syntax? When doing it in this way, you now are free to dynamically pass both the row quantity and the column quantity. But yet again, you see that in order to access the coordinates of your array, it is a single square bracket, and you have to perform the arithmetic to get to row I, column j. Now we'll see the other way of doing this, which is by making multiple calls to malloc. And so here we're going to truly have, an array of arrays. So that kind of explains why the type declaration here is int star star. Effectively, this is going to be an array of pointers to integers. So it certainly is also where, when you get to pointers, kind of people's heads very reasonably start spinning. The idea, I think they have a diagram here. So maybe the diagram is a nice place to start. So you're going to initially have this 2D array. It is declared as int star star, so that basically means it is a pointer to point, right? So this is a pointer to pointers, right? Each one of these is also going to be a pointer, and those point to the rows. So it is a pointer to pointers to integers. And here's what we need to do, right? We now need to malloc that pointer, but what's the size of the thing that it's pointing to? Well, it's an array of pointers to integers, right? So we need to say size of int star in parens so that it computes the size of a pointer to an integer. And then there are n of them, n being the number of rows. So by the way, I guess that's worth emphasizing at this point that this is a pointer to pointers, but those pointers are pointing to, some base address of an array, but what that represents is the row. So these, although they are drawn vertically like this, don't be fooled, these are meant to be the rows of the array. As of this, malloc, though, all you have is a pointer to addresses, or at least things that could hold addresses, but they do not yet hold addresses. And moreover, these rows of data have not yet been carved out, so we need them. And that is why we need to follow this up with a for loop over each one of these addresses. We want to grab some specific address, at least some specific place where we want to put an address. And there we would like to make a call to malloc so that simultaneously this row comes into existence because we are allocating it, and its address is put into this, place, so that we can basically follow it over to its destination. So by calling that malloc, we can now actually get to here, and then from here we can get to here. Now, as I've said already, and I'll just briefly repeat it, because this calls many calls to malloc. By the way, how many calls to malloc? Well, certainly this for loop makes n calls to malloc, and then here we get one more, so this is n plus 1 calls to malloc. Because we make several calls to malloc, these various arrays, right, this will all be contiguous, but it will not necessarily be contiguous with this right here, and that will not be contiguous with this, and so on, so that this data is now probably or possibly spread all over your hardware. And because the computer has to sort of scan, follow these faraway locations, it can cause your programs to slow. If you're dealing with small amounts of data, you won't even notice it, but if you're dealing with large amounts of data, then you can start to notice the slowdown. But once having declared things this way, you can use the bracket syntax to access rows and columns again. In this way, right, doing it this way, again, because it is dynamic, the thing that changes when passing these into functions is that the argument is now declared as int star star, and you are free to dynamically pass in the rows and the columns, but yet again, you see that you get, right, with this method, you get to use the bracket notation for accessing coordinates.